Welcome back to part 2 of central difference in time, central difference in space to solve advection equation, or so-called Leapfrog. Alright, so the equation we were trying to solve was du dt plus v du dx equals 0. We showed that if you use von Neumann stability analysis, we end up getting an equation like this, where we assume if alpha is less than 1, then the c, or the magnitude of c raised to the second power, is always equal to 1, which leads to a stable, conditionally stable final difference scheme. Conditionally because it's conditioned on alpha. Now what if alpha is bigger than 1? If alpha is bigger than 1, then when we want to find the complex conjugate of this, because this thing below, below the square root is, or under the square root is negative, then this is imaginary as well. So we're going to convert this into a positive under the square root and then times the complex variable I. So we're going to get plus minus alpha times sine squared minus 1 and times I minus alpha sine k del x times I again. So now both are imaginary. Now we're going to assume that our alpha times sine is bigger than 1. So we're going to assume this for now. This is our hypothesis. So assuming that, we're gonna have two imaginary numbers, we're going to add them up, and then when you get the magnitude of c squared, which means this thing times its complex conjugate. And complex conjugate of this would be just flipping the sign of every imaginary term, which means we need to flip this sign here. We need to flip the signs here too. So what we get is this term, which is alpha sine, plus minus this term. Okay, then raised to the second power, we're going to drop I, because I raised to the second power is -1, and because we're doing the absolute value of that, so that's going to be plus 1. Anyway, so now we're going to complete this square, or maybe open it up. So you get the first term squared plus the second term squared, which is another alpha squared sine squared, so plus this guy's going to be 2 alpha squared sine squared and then minus 1, and then plus minus 2 times the first term times the second term, which is this. Now if you assume alpha times sine k del x is beta, then we're going to rewrite this equation as 2 beta squared minus 1, so this is 2 beta squared minus 1 plus minus 2 times beta, and then square root of beta squared minus 1. Okay, now, again, the goal is to prove that this is either below or less than or bigger than 1. Okay, so if we assume that beta is bigger than 1, that means this is positive, and this is also positive. So what we can do is we can plot this function. You can plot this function basically against beta. So now I have beta on the horizontal axis. On the vertical axis, I have my magnitude squared. So if you plot this outside, or if beta is bigger than 1 or less than -1, this one is always positive. So then the whole thing is going to be a real number. So our range or domain of beta is going to be outside of plus minus 1. So here is -1, here's +1. We're going to plot everything outside this domain, which means bigger than 1 or less than -1. Alright, so if beta is bigger than 1 and we get the positive branch, so this is definitely bigger than 1, because if beta is bigger than 1, 2 beta squared is bigger than 2 minus 1, this is bigger than 1 plus a positive number, so it's definitely bigger than 1. So that's the plus branch. And if you follow the minus branch, then you get basically less than 1. At exactly beta equal 1, you get 0 here and you get 1 here. So at exactly beta equals plus minus 1, you get exactly c squared equal to 1. So this shows that if beta is bigger than 1, the magnitude of c squared is bigger than 1. If beta is less than -1, then the magnitude is less than 1. So the condition that we had before, where if beta is bigger than 1, we might land on this branch, which is giving us the magnitude of c squared is bigger than 1. So for beta bigger than 1, we get unstable. All right, so then go back to here. If alpha bigger than 1, we get unstable, because in that case, if alpha is bigger than 1, beta could be bigger than 1, and if beta is bigger than 1, we get unstable. So overall, if alpha is bigger than 1, we are still getting unstable method. So overall, if you put this condition, alpha bigger than 1, which we saw in the last video, and alpha bigger than 1 in this video, we conclude that the only way we can get a stable method is to have alpha less than 1, because this leads to unstable. So stability region is alpha less than 1. So central difference in time, central difference in the space for advection equation gives us conditionally stable. And the condition is alpha should be less than 1. So what was alpha, by the way? So we go back. Alpha is our non-dimensionalized velocity, v times dt over del x. All right. So I'm going to skip the next 2 pages of the notes. These are different ways of proving why it's unstable. And we're going to jump into the concept of why this is called Leapfrog. All right. So if you remember the numerical technique we used, maybe you have to go back and revisit that equation one more time. So this is the, well, I can go back to here. So this is Leapfrog method that we started with. To calculate, well, we can actually look at the simplified version of it, which is right here. So to calculate the variable at point j, x at x of j and time n plus 1, we need to know the variable at point j and time n minus 1, so j and n minus 1, and then the variables at j plus 1, j minus 1 at time n. So we need to know 3 values to calculate the variable at time n plus 1 and xj. So we need to know n minus 1 on j, n on j plus 1, and n on j minus 1. So let's go to that graph and see how we can represent these with the grid. So here's the grid of time space coordinates. So this is the spatial coordinate, that's the time coordinate. Our time index is, I'm showing the time index at n minus 1, tn, and tn plus 1. At the same time, I'm showing the spatial coordinates at j minus 1, j, and j plus 1. So if you remember from the Leapfrog method, to calculate the variable at n plus 1 and j, so here's j, here's n plus 1, to calculate this variable at this grid point in time and space, we need to know at time tn and xj minus 1, we need to know time tn and xj plus 1. We also need to know the variable at time tn minus 1 and xj. So these are the 3 terms in that difference equation we showed before. So we're going to use these 3 to calculate that one. So if you look at this grid of 3 by 3, out of these 9 points, I used only 4 points. Basically, I skipped over the middle one. So you can expand this over the whole grid of time and space, and what you see is the following. So we can split this grid of time-space plane to 2 sets of grids, or 2 sets of grid points, the red ones and the black ones. So basically, if you look at that, we get every other one red in every row, and every other one is black. So what we saw is that the information that we get from the red never use the information that we get from the black, and vice versa. In other words, the information passed through the red points never crossed information passed through the black points. And that's why it's called Leapfrog, because the information jumps from this red point to that point, and then from this red point to that point, and so forth. And then from the black point, the information jumps from here to here, and from here to here. So we never actually cross. When we go over the red points, we never see the black ones, and when we go over the black ones, we never see the red ones. So we have two completely separate grid points, which never crosstalk. So this is exactly Leapfrog. And if you remember from childhood, you might have played this game where let me make this bigger. So here are the kids. They're playing actually Leapfrog. This is a well-known childhood game. That so basically, if this this person wants to basically play the game, so what he does is he jumps over her. So that means if you think of these as grid points, I can think of this as a black grid point, this is red, and this is black. So this jumps over this and then becomes the next person. So that's why it leapfrog or leaps over every other points or every other game player. So that's exactly the same thing we are saying in our numerical technique, and that's why it's called Leapfrog. So so far we looked at central difference in time and central difference in space, and we saw that this is conditionally stable. Now, to basically improve this method, two guys came about and proposed a different method, which is called Lax-Friedrichs. So Lax-Friedrichs proposed that in the Leapfrog, or actually in the they actually went back to the original forward Euler in time and central difference in the space. And they proposed that in forward in time, we can replace the u at n and j with the average of u and at j plus 1 and j minus 1. So to recall, let's go back to forward Euler in time and central in the space. So I'm going to go back to the page that we talked about central difference in the space and forward in time. So this is it. So we started actually from forward Euler. This is forward Euler in time, and this is central difference in the space because I plus 1, I minus 1 here, and then here is n plus 1 and a. So forward in time, central in the space. Now we're going to get this method and replace this term by the average of two spatial variables, I plus 1 and I minus 1, both at time tn. So let's go back to Lax-Friedrich. So here's Lax-Friedrich, and we replace that un and xj with xj plus 1 and j minus 1 and get the average of it. Alright, so now we have we have two sets of variables, one at tn plus 1 and one at tn. So we're going to move all the n variables to the right side and keep everything at n plus 1 on the left side. So we're going to get n plus 1j, you get 1/2 nj plus 1 nj minus 1, and then minus multiply 2 by del t, you get v del t over 2 del x, nj plus 1 and nj minus 1 here. Alright, so this is our Lax-Friedrichs. Now we're going to replace our well-known v del t over del x by alpha, so we get 1 minus alpha over 2 over here. So this is a second order in the space, by the way, because we're using central difference in spatial coordinates. Alright. This is also first order in time, it's not second order in time. First order in time because actually we didn't really use central difference in time. We just replaced, it is first order in time because we started from forward Euler, we just replaced one of the term by average of the other two terms.